Today we are going to be looking at our first learning target for our new unit, which is I can define and represent transformations using various tools. So if you recall possibly from our 8th grade summer class, a transformation is an operation that maps an original figure called the pre-image onto a new figure called the image. So if you look at the graph on the left, we see that we have triangle ABC, and that is the pre-image, and then we have a second triangle, and if you look closely, you'll see that it has A with a dash next to it, B with a dash next to it, and C with a dash. That's read as triangle A prime, B prime, C prime, and that is our image of the pre-image ABC. A transformation can change the position, the orientation, or the size of a figure. So for the next couple of days, we're really going to be focusing on rigid motions. And so rigid motions, when a transformation or when we perform a transformation that preserves the size and shape of a figure, that's a rigid motion. So all corresponding sides and angles of the pre-image and image are congruent when we are performing rigid motions. So examples of transformations that are rigid motions are translations, which we will be looking at today, reflections, which we will be looking at tomorrow, and rotations. So a translation is to vertically or horizontally slide a figure from one location to another. So when we do that, we are sometimes given coordinate notation. So with coordinate notation, you take your original ordered pair, which is x comma y, and then you'll see that an operation is being performed to the x value and the y value. So we'll represent that as x plus h and then y plus k. And h is going to represent the horizontal shift, and k is going to represent the vertical shift. So if we look at example 1, we have two examples here. It says graph and label each figure and its image under the given translation. Identify the coordinates of the image. So go ahead right now, pause your video and graph the rectangle QRST, and then I will come back and we will look at how to translate this. Okay, so your pre-image QRST should look like the one that I have on my graph. And if we are going to translate this, we are going to look at the coordinate notation here. So our ordered pair from our pre-image, we are going to be adding 5 to the x value, which would be to be moving to the right 5 spaces. And then we would be adding 7 to the y value, which would be to move up 7 spaces. So we can do this one of two ways. You can do the math of it. So if I look at my ordered pair at Q, which is -6, -1, if I take -6 and I add 5, then I get -1. And if I take -1 plus 7, I get 6. So the translated value of the pre-image Q would be at -1, 6. And when I label that, I would put Q prime. Do not forget to label that when you are doing this on your own. If I did not want to do it the mathematical way, I could take my second pre-image R, and I could count right 5 spaces. So 1, 2, 3, 4, 5, and then up 7. 1, 2, 3, 4, 5, 6, 7. And I would get that the image of R prime, would be right there. Okay, go ahead, translate pre-image T and S, and then check back with me. I'm going to pause the video, and you should too. Okay, so you can see, hopefully, that your pre-image and image are congruent figures. T ended up mapping to 3, 0, or the image of T ended up mapping to 3, 0, and the image of S ended up mapping to 6, 2. So again, if when you do this, you notice that your figures are not congruent, something went wrong, go back and check your work. Okay, go ahead and try the next example on your own. I will pause the video and I will put my work together and check to see if you were able to get it right. Good luck. Okay, so looking at your example, you would have graphed the pre-image triangle CDE, and then if you look at our coordinate notation, we are going to be subtracting 3 from our x value. However, the y coordinate is going to, or the y value is going to stay the same. So that would just be moving your x values to the left 3 places. And we can see that we have triangle C prime, D prime, and E prime that is just shifted over to the left 3 spaces. And we can note our coordinates at the bottom of the graph. So C prime is at -1, 7. D prime is at 4, 4. I take that back. Those are not correct. Hold on one moment. Okay, we're back with you. It wouldn't be a Malloy video if she didn't make a mistake. So C prime is at -1, -1. D prime is at 4, -4. And E prime is at 1, -6. Okay, so again, make sure that you have labeled your image points with the prime, or sometimes you'll hear me refer to it as a tick mark, so that we can distinguish between the pre-image and the image. Okay, so moving on, we're going to talk about translating using vectors. So in the previous examples, we were translating using coordinate notation. Now we're going to be using what is called a vector. So a vector is a quantity with both direction and magnitude. And magnitude is just another word for size. So a vector is represented in the coordinate plane by an arrow drawn from an initial point, which we'll refer to as P in our diagram to the left, and then to a terminal point, which in our diagram is referred to as Q. So we would denote the vector as ray PQ, and we would read it as vector PQ. So the component form of a vector is written as vector PQ, and then we would have some arrow-like brackets, an A, comma, B, where A is the horizontal component and B is the vertical component. So if we're looking at our diagram here, the horizontal component is 4 units and the vertical component is 7 units. And we would just be counting those boxes going up. So 1, 2, 3, 4, 5, 6, 7. And same with our horizontal component. So the component form of the vector to the left is vector PQ is equal to 4, 7. And again, we use those more arrow-like. They look very similar to the greater than or less than symbols, however, they're a little bit more open than the greater than or less than symbols. Okay, so let's looking at example 2, name each vector, then write the vector in component form. So we have vector WV here, and we first want to look at our horizontal component and our vertical component. So if we're counting, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our horizontal component is 9, and then our vertical component is 3. So our component form would be vector WV is equal to 9, 3. Okay, go ahead and try the next 2 parts of this example, and we will come back and compare answers. So pause your video right now. Okay, so looking at our last 2 pieces of this example, the middle example, notice that it's vector BA. I can tell that because the initial point is at B, and then the arrow that is drawn is pointing to A, which makes A our terminal point. So that's going to be the second value that's labeled. Okay, and then we can see that from B, the horizontal component is going to the left 5, which would be a -5 motion, and then we're going up 1, so that would be a +1. So the vector component would be -5, 1. In the last example, for example 2, the last portion of example 2, we have vector HG, and again we can tell that H is our initial point because the arrow is going away from 8, or the vector is moving away from H to G, which would be our terminal point, and it is moving horizontally, -11 spaces, and it is not moving up or down, so our vector component would be at -11, 0. Alright, so if we go to example 3, it says graph and label each figure and its image under the translation along the given vector. Identify the coordinates of the image. So triangle STU with vertices, well, you guys can read, and we're going to be translating it along the vector -1, -5. Okay, so looking at example 3, graph and label each figure and its image under the translation along the given vector. Identify the coordinates of the image. So we are going to graph triangle STU with the vertices given and translate it with the vector -1, -5. So I will adjust these for your notes, but go ahead and graph that pre-image and then graph the vector, and then we will come back together and finish the example together. So pause your video now and get the pre-image and vector onto your graph. Okay, so you can see if you graph your pre-image triangle STU, and then for your vectors, the vectors are going to be coming from each ordered pair, or each point, because each point is going to be translated. So we drew in a vector that would follow the slope of -1 to the left and 5 down, or 1 to the left, 5 down, and then where those vectors land, those terminal points, are going to be where your image points are. And again, remember that you need to create or add the tick marks on your labels. So go ahead and connect those points, and we can see that we have a congruent figure to our pre-image triangle STU. Okay, if we look at our last example 4 here, describe the translation that maps each pre-image to its image in A coordinate notation and then B as a vector in component form. Okay, so we're going to go ahead and take a look at first identifying which is your pre-image, which is your image. Okay, so our pre-image, we notice that there are no tick marks on the pre-image that is more to the left, so that's going to be the pre-image, and then our image, we see those tick marks for D prime, so that is going to be our image. So we need to identify what is our horizontal shift and then what is our vertical shift. So we can do that basically by counting. So if I am looking at my horizontal shift first, I'm counting to the right, 1, 2, 3, 4, 5, 6, 7. Okay, so that would be in my coordinate notation. I would be adding 7 to X, and then I would be going 1, 2, 3, 4 up, so that would also be adding, so Y plus 4. Then if I am looking in my vector and component form, I'm going to be using those values. So I have 7, 4. Okay, because I am moving horizontally 7 and then vertically 4. All right, your practice for this notes packet is located on Delta Math, so go ahead, log into that, and complete the examples or the problems that you are required there. And be sure to check in with me on Zoom if you have any questions. I'd be happy to help answer those for you. Okay, good luck.